The most powerful rocket ever built lifted off on a clear April morning in 2023, and less than 4 minutes later, it was gone. Not because engineers were careless, not because the technology was foolish, but because flight testing at the absolute frontier of engineering is, by design, a conversation between ambition and reality. And sometimes reality answers loudly. This is the story of Starship's first integrated flight test, what it was meant to prove, what it revealed instead, and why the people who built it considered the outcome a turning point rather than simply a failure. To understand what SpaceX was attempting, you have to understand the scale. For roughly 50 years, the Soviet Union's N-1 rocket held the record as the most powerful launch vehicle ever flown. It was a record that had stood through the entire arc of the Space Shuttle program, through the construction of the International Space Station, through the modern commercial launch revolution. On April 20, 2023, at SpaceX's Starbase facility in Boca Chica, Texas, a vehicle called Starship broke that record simply by leaving the ground. The question engineers wanted to answer was deceptively straightforward. Could the Super Heavy booster and the Starship upper stage, two enormous and separately developed systems, function as a single integrated launch vehicle? This was not a question anyone could answer on paper, in simulation, or in component testing alone. The only way to know was to fly the complete stack together for the first time. That is why this test was formally designated the first integrated flight test. The emphasis on the word integrated matters. Every previous test had evaluated pieces. This one evaluated the machine as a whole. From an engineering standpoint, the challenge of combining a booster and an upper stage of this class is not simply about adding power. It is about managing an enormous web of interacting systems, propulsion, structural loads, aerodynamic forces, software coordination, and fuel management, all of which behave differently when they are asked to work together rather than in isolation. Think of it less like assembling furniture from a manual and more like conducting two orchestras simultaneously, where neither has ever played with the other, and the concert hall itself is shaking. The goal was never a flawless operational flight. The stated purpose was to gather data, stress the systems, and learn what would only reveal itself under real flight conditions. There were genuine reasons for confidence going into the test. The Super Heavy booster had been designed and constructed to a specification that demanded it outperform every rocket that came before it in terms of thrust. Individual engine tests had proceeded. The launch infrastructure at Boca Chica had been developed specifically for a vehicle of this size. The team had worked through an extensive series of pre-flight evaluations, and SpaceX had a documented organizational culture of treating each successive test as a data point rather than a pass-fail judgment, a philosophy that, in prior programs, had allowed iterative development to succeed where more conservative approaches had stalled. That context matters when evaluating what came next. Even before the flight, the constraints of operating at this scale were apparent. The launch infrastructure itself was under unprecedented stress. A vehicle generating thrust figures no ground facility had previously handled creates engineering demands that are not always fully predictable in advance. The environment around the launch mount, the behavior of materials, the interaction between exhaust plume and ground structure, these were known areas of uncertainty, and engineers had taken steps to address them. Whether those steps were sufficient was itself a question the test would help answer. There were also the inherent unknowns of first-flight aerodynamics and integrated propulsion behavior. By definition, no prior dataset fully covered this configuration. The vehicle lifted off and initially performed in ways that confirmed it was, in fact, the most powerful rocket ever flown. The record that had stood since the Cold War era was broken in the first seconds of flight. For observers and engineers alike, the sheer fact of the vehicle clearing the launch mount and ascending was itself a significant data point. Then, within the first few minutes, things began to go wrong. The vehicle failed to achieve the stage separation that would have marked a successful transition between the booster phase and the upper stage flight. The flight termination system, a safety mechanism designed specifically to protect public safety in the event of an uncontrolled vehicle, was activated. The vehicle was destroyed less than 4 minutes after liftoff. The cascade of events between liftoff and destruction involved propulsion system behavior during the flight that did not match nominal predictions. The precise sequence of what failed, and in what order, was exactly the kind of information the data recorders and ground telemetry were designed to capture. Some of that data was recovered, some was not. Investigation into what happened drew on telemetry, structural analysis, and review of the launch site. The damage to the ground launch infrastructure became one of the most discussed aspects of the aftermath. The interaction between the exhaust plume and the launch mount had produced effects more severe than pre-test models had fully anticipated. This was not a minor footnote. It shaped how the next test campaign would be approached. There were competing technical explanations for the sequence of propulsion events during the flight itself. Engineers worked through the data to distinguish between what had caused the initial anomalies and what had followed as a consequence. That distinction matters in any accident investigation. Confusing a symptom for a root cause leads to fixes that don't solve the underlying problem. The root causes, as they emerged from the investigation, operated on multiple levels. Technically, the behavior of an unprecedented propulsion and structural system under real flight loads had not been fully captured by pre-flight models. That is not a criticism. It is inherent to first-of-kind testing. But it does mean that the margin between the predicted envelope and the actual envelope was smaller than the team had accounted for in at least some areas. Organizationally, the timeline and decision-making around launch infrastructure preparation came under scrutiny. The ground systems that support a launch are not passive. They interact with the vehicle in consequential ways, and underestimating that interaction turned out to matter. From an ethical and oversight standpoint, the Federal Aviation Administration was involved in the licensing and review process. Regulatory coordination between a company pushing development timelines and a regulator assessing public safety risk is always a tension, and this test sat squarely inside that tension. What changed after the test was substantive. The launch infrastructure was redesigned and reinforced. A steel water deluge plate system, intended to manage the energy of the exhaust plume at the launch mount, was added, a direct response to the damage the first test had revealed. Propulsion system configurations were revisited based on the flight data. Flight software and termination system logic were reviewed. The subsequent flight tests were conducted under modified conditions that reflected what the first test had taught. That is the structure of iterative development working as intended, not because the failure was acceptable, but because the failure was informative. There is a temptation, when watching a rocket worth enormous resources destroyed in under 4 minutes, to ask whether the test was worth it. The honest answer is that it depends entirely on what you believe first flight testing is for. If a test must succeed to be valuable, then no, it was not worth it. If a test must generate data that could not be obtained any other way, then the 4 minutes of flight produced something no simulation could have provided. What this episode illustrates is not that the engineers failed. It is that the gap between a model of a system and the system itself is a gap that only reality can fully measure. Every engineering discipline that has produced the infrastructure of modern life, aircraft, bridges, medical devices, spacecraft, was shaped in part by tests that went wrong and revealed something unexpected. The record broken on that April morning was not just the N-1's thrust record. It was a record of what was unknown about operating at that scale. And in engineering, knowing what you don't know is often the most valuable thing a test can return. This content is for educational purposes only. Do not attempt to recreate any described experiment or procedure.